treated ligands as a point charge or dipole and does not take into the account the covalent bonding in complex. Instead, it regards the bonding purely ionic. The physical measurements such as electron spin resonance (ESR) or electron paramagnetic (APR), nuclear magnetic resonance (NMR), nuclear quadrupole resonance in QR, and Rasch parameter calculation from electronic spectra give evidence in favor of covalent bonding and coordination compound. The covalent bonding in complex has been explained by ligand field theory (LFT). According to ligand field theory, covalent bond between metal and ligand are formed by the linear combination of the metal atomic orbitals and ligand groups orbitals (LGOs). The symmetry of ligand groups orbitals must match the symmetry of the metal atomic orbital such that there is positive overlapping of LGOs with metal orbital along the bonding axis. Sigma bond in octahedral complexes. In octahedral complexes, the ligands are approaching the metal atoms on X, Y, and Z axis. Therefore, ligand group orbitals will overlap with metals orbitals along the octahedral bonding axis to form sigma bonds. The metal cation has in its valence shell 1 ns, 3 np, and 5 n-1 d orbitals. The octahedral symmetry has transformed s orbital into a1 gp orbital into t1u dxy dyz and dzx orbital into t2g dx square y square and dz square orbital into eg sets. Metal orbital s symmetry a1g, metal orbital px py pz symmetry will be t1u, metal orbital dxy dyz dzx symmetry will be t2g, metal orbital dx square y square dz square symmetry will be eg. Since a1g orbital is spherical in shape, therefore it can overlap with ligand group orbital on all axes. The T1u and Eg orbitals are pointing along the axis. Therefore, this orbital can form sigma bond on octahedral axis by overlapping with ligand group orbitals. The T2g orbital lie in between the axes. Therefore, these orbitals are not capable to overlap with ligand groups orbital to form sigma bonds. Therefore, out of 9 metal orbitals, only 6, 1 A1G, 3 T1U, and 2 EG orbital participate in sigma bonding formation. The T2G orbitals are considered to be non-bonding molecular orbital in octahedral complex, where there is no possibility of pi bonding. If the ligand has orbital of same symmetry as that of metal T2G orbital, then T2G metal orbital will be involved in sigma in pi bond. Now the question arises that what are the ligand group orbitals and how can this be constructed? Each of the 6 equivalent ligand atoms contributes an atomic orbital or hybrid atomic orbital to form sigma bond in an octahedral complex. The 6 atomic or hybrid orbitals of 6 ligand are pointing along plus x plus y minus y plus z and minus z axis, which have been represented as sigma x, sigma minus x, sigma y, sigma minus y, sigma z, and sigma minus z respectively. Figure 4.19. Sigma z, sigma y, sigma x, sigma minus z, sigma minus y, sigma minus x. 6 ligand orbitals in octahedral symmetry. The sigma x, sigma minus x, sigma y, sigma minus y, sigma z, and sigma minus z orbital of ligand are combined together linearly to form a set of ligand group orbital of the required symmetry to overlap with the A1G, T1U, and EG orbital of metal. Since the wave function of A1G orbital has same sign, which is taken to be positive everywhere, the 6 ligands therefore can overlap equally with this orbital, and each ligand orbital must also have positive sign. Thus, A1G ligand groups orbital can be constructed by additive linear combinations of 6 ligand orbitals. Epsilon A1G is equal to 1 upon square root 6 in bracket sigma x plus sigma minus x plus sigma y plus sigma minus y plus sigma z plus sigma minus z in bracket out of bracket a1g, where 1 upon root 6 is normalization constant and sigma and epsilon and sigma are the wave function of ligand group orbitals and contributing ligand orbital. Since wave functions of one lobe of each of the px, py and pz orbitals has positive sign and other has negative sign, therefore epsilon x equal to 1 upon root 2 sigma x minus sigma minus x epsilon y is equal to 1 by root 2 sigma y minus sigma minus y and sigma z and epsilon z is equal to 1 upon square root 2 in bracket sigma z minus sigma minus z. The two opposite lobes of the x square y square orbital have positive sign and the other two opposite lobes have negative sign. Therefore, epsilon x square minus y square is equal to 1 upon 2 in bracket sigma x plus sigma minus x minus sigma y minus sigma minus y. Z y x a1g z y x px z y x z py yx z py x t1u pz z y x sigma yx e.g. dx square y square z y and x dz square z y x e.g. The dz square orbitals obtained by the combination of two dependent orbitals v dz square x square and dz square y square. The dz square minus x square plus dz square minus y square is equal to d 2z square minus x square minus y square. The dz square is actually the 2dz square minus x square minus y square. Therefore, the ligand group orbital that match the dz square orbital correspond to the d2z square minus x square minus y square. Epsilon z square is equal to 1 upon 2 root 3 in bracket 2 sigma z plus 2 sigma minus z minus sigma x minus sigma minus x minus sigma y minus sigma minus y. The ligand group orbitals where their symmetry match with metal orbital are shown in figure 4.20. This 6 combination account for all ligand orbital to be of sigma symmetry. None of these ligand group orbitals have the symmetry of metal T2G orbitals. Therefore, the latter do not participate in sigma bonding. From the symmetry property of octahedral complex, it is observed that metal and ligand A1G orbital will overlap to give two molecular orbitals, one bonding A1G and one anti-bonding A1G star. The triply degenerate metal and ligand T1U orbital will overlap to give 6 molecular orbitals, 3 degenerate bonding T1U and 3 degenerate anti-bonding T1U star. The doubly degenerate metals and ligand EG orbital will overlap to give 4 molecular orbitals, 2 degenerate bonding EG and 2 degenerate anti-bonding EG star. Therefore, there are 6 bonding and 6 anti-bonding molecular orbitals. In a system without pi bonding, the 3 triply degenerate metal T2G orbital are non-bonding and have same energy as in free metal cation. The overlap of metal A1G and T1U orbital with ligand group orbital is more extensive than that of E1 EG orbitals. Therefore, there are large difference in energy between the resulting A1G and A1G star and T1U and T1U star bonding and anti-bonding molecular orbital. Therefore, the A1G and T1U bonding molecular orbital are lower in energy and A1G star and T1U star anti-bonding molecular orbital are of highest energy. The EG and EG star molecular orbital have less energy difference because of poorer overlap between the metal and ligand EG orbital. Therefore, we can say that more is the overlap larger will be the separation and more will be covalent character. The energy difference between T2G and EG molecular orbital is equal to delta zero as given by the crystal field theory. It is assumed that a given molecular orbital has a character associated with atomic orbital which is nearest in energy. For most of the ligand sigma orbitals are derived from the atomic orbital, which have lower energy than the metal d orbitals. Therefore, the 6 bonding molecular orbital 1 A1G, 3 T1U, and 2 EG orbital of the octahedral complex have primarily the character of ligand orbitals, but also have some character of metal orbital from which they are derived. In fact, the ligand 2 leaks on to the metal cation or atom. On the other hand, the antibonding molecular orbital Eg star, A1G star, and T1U star have mainly the character of corresponding metal orbital, but are somewhat delocalized on to the ligand. Since the T2G orbital are not involved in sigma bonding, therefore these are non-bonding and their energy is same as in free metal cation. This orbital have pure metal d orbital character in octahedral complex. The 6 ligand provides 6 pair of electrons which all are accommodated in the bonding molecular orbitals. These electrons are mainly retained onto the ligand in the complex just as described by crystal field theory CFT. In addition to the 6 pair of electrons provided by the ligand, there will always be dn electron available on the metal atom or cation which occupy the non-bonding, the T2G and anti-bonding Eg star orbital. The n electron provided by the metal ion retained mainly onto the metal ion. The distribution of the metal d electron in T2G and Eg star orbital are similar as described by CFT. But the basic difference is that in LFT, the T2G Eg star orbital are not confined completely to the metal ion, whereas in the CFT, the d electrons are completely confined to the metal ion. In octahedral complex, there are total 12 plus dn electron to be placed in molecular orbital, where dn represents the number of metal d electron. The distribution of 12 plus dn electron in molecular orbital will be A1G2, T1U6, EG4, T2G, P, EGQ star, where P plus N is equal to Q. A1G, T1U, EG bonding molecular orbital, T2G, EG star, A1G non-bonding molecular orbital, A1G star, T1U star anti-bonding molecular orbitals. The LFT also give them interpretations of high spin and low spin complex depending on the magnitude of delta zero and the pairing energy, which is similar to that given by the CFT. For low spin complex, delta zero is greater than P. For high spin complex, delta zero is smaller than P. Order of energy of molecular orbital and distribution of electron in them. For low spin complex, the magnitude of delta zero is large enough. Therefore, the energy of molecular orbitals follow the order. A1G smaller than T1U, smaller than EG, smaller than T2G, smaller than EG star, smaller than A1G star, smaller than T1U star. For example, the complex by NH363+, which is a low spin complex, have total 18 valence electron, 12 from the 6 ammonia ligand and 6 are metal d electron. The electronic configuration is A1G2, T1U6, EG4, T2G6. B. For high spin complex, the magnitude of delta zero is small, therefore the energy of T2G and EG star orbital are assumed to be similar. Therefore, energy of molecular orbital of high spin complex follow the order. A1G is smaller than T1U, smaller than EG, smaller than T2G, smaller than EG star, smaller than A1G star, smaller than T1U star. For example, for cobalt F63 minus complex ion, which is a high spin complex, there are total 80 electrons in valence shell. For this complex, electronic distribution is A1G2, T1U6, EG4, T2G4, EG star 2. Figure 4.21 indicate that all the octahedral complex should have, in addition to the DD transitions, at least one ligand to metal charge transfer band, that is transition of an electron from predominantly ligand orbitals to predominantly metal orbital. The intense charge transfer bands are observed in ultraviolet or sometimes invisible region in many complex corresponding to transition of sigma electron to vacant T2G or EG star or both to high energy orbital. Pi bonding in octahedral complex. In addition to metal ligand, sigma interaction, many ligands which have orbitals with pi symmetry with respect to octahedral axis are capable for pi bonding interaction with the metal atoms or cations. The pi bonding will be significant if the metal and the ligand orbital have proper pi symmetry and comparable size and energy. The metal and ligand orbital involving in pi bonding are perpendicular to the ML axis. In an octahedral complex, there are 12 ligand groups, orbital capable of pi interaction. These ligand group orbitals belong to the four symmetry classes T1G, T2G, T1U, and T2U. On the other hand, the transition metal cation in an octahedral complex has two types of orbital, T1U and T2G, which are of correct symmetry for pi bonding. The T1G and T2U ligand co-orbitals are non-bonding because there are no meta-orbital of this symmetry. The meta-orbital of T1U symmetry are directed at the ligand and therefore involved in sigma bonding. Therefore, these orbitals are unavailable for pi bonding. The T2G ligand groups orbital and meta-orbital of same symmetry, that is T2G can form metal ligand bimolecular orbital, that is 3 bonding molecular. The T1G and T2U ligand group orbital are non-bonding because there are no meta-orbital of these symmetries. Meta-orbital of T1U symmetry are directed at the ligand and therefore involved in sigma bonding. Therefore, these orbitals are unavailable for pi bonding. The T2G ligand groups orbital and the metal orbital of the same symmetry, that is T2G, can form metal ligands sigma molecular orbital, that is 3 bonding molecular orbital T2G and 3 antibonding molecular orbital T2G star. The bonding molecular orbital T2G are of lower energy and antibonding molecular orbital T2G star of high energy than the atomic orbital. Both bonding and antibonding molecular orbital are triply degenerate. In octahedral complex, the ligand group's orbital corresponding to T2G symmetry may be p pi, d pi, pi star or sigma star. Therefore, there may be 4 types of pi interaction: 1 d pi p pi, 2 d pi d pi, 3 d pi pi star, and 4 d pi sigma star. First, d pi p pi bonding. In this type of pi bonding, the ligand orbitals are formed by combination of p orbital perpendicular to sigma bond axis of donor atom of ligand. Figure 4.22a. The d pi p pi bond are formed by donation of electron from p pi orbital of ligand to empty d pi orbital of the metal. The p pi orbital always filled and are found in F: fluorine minus, chloride minus, bromine minus, iodine minus, O2 minus, RO minus, Iris minus, etc. The 2 d pi bonding. In d pi bonding, the filled d orbital of metal overlap with the empty d orbital of the ligand. Figure 4.22b. The ligands such as R3p, R2s, R3s have the empty d orbital or pi symmetry. 3. D pi pi star bonding. The d pi pi star bond are formed when filled d orbital of metal cation or atom overlaps with empty pi star, the pi anti-bonding of the ligand. The ligand having the empty pi star orbitals are carbon monoxide Cn minus, pyridine, orthophenanthroline, ethylene, nitrogen dioxide minus. Fifth, d pi sigma star bonding. The d pi sigma star bond are formed when the filled d orbital of the metal cation overlap with empty sigma anti-bonding sigma star of the ligand. The ligand having the empty sigma star orbital are H2 hydrogen R3p trialkyl phosphoalkene etc. In a trialkyl phosphor, the sigma star orbital are of p phosphocarbon bonds. A is d pi p pi bonding, B is d pi bonding, C is d pi star bonding, and D is d pi sigma star bonding. If the ligand T2G orbital are filled and are of lower energy than the partly filled metal T2G orbital, then the ligand T2G orbital overlap with the metal T2G orbital to give bonding T2G molecular orbital. That is T2G of lower energy than ligand group orbitals and antibody molecular orbitals. That is T2G star of higher energy relative to the non-bonding T2G orbitals of lower energy than ligand. Sorry. If the ligand T2G orbital are filled and are of lower energy than partly filled metal T2G orbital, then the ligand T2G orbital overlap with the metal T2G orbital to give bonding T2G molecular orbital, that is T2G of lower energy than ligand group orbitals and antibody molecular orbitals, that is T2G star of higher energy relative to the non-bonding T2G orbital of sigma bonding complex, the ligand having filled T2G ligand group orbital of lower energy. Then the metal d orbitals are fluoride minus iron, chlorine minus iron, bromine minus iron, Rd minus iron, H2O, H2 minus etc. This ligand having filled T2G ligand group orbitals are called pi donor ligand. Since the ligand group orbitals are of lower energy than that metal T2G orbital, therefore the bonding molecular orbital have the character of ligand group orbitals and the antibody molecular orbitals have the character of metal T2G orbitals. Therefore, the electron supplied by the ligand T2G orbital will fill the pi bonding molecular orbital, and the electron from the metal T2G orbital will fill the pi anti-bonding orbitals. The EG stars are not affected by pi bonding, and T2G metal orbital become anti-bonding and hence are raised closer in energy to the metal EG star. Anti-bonding orbital is the energy difference delta zero between the T2G star and EG star is relative to different where metal ligand